There we go. Now, according to my schedule, exam 2 is chapter 3 and chapter 4. And we have 1, 2, 3. We've got it up to 3 periods that we can use to cover the material. And that'll still give us a review session. If we can get through all of it, then in 2, then that'll give us 2 review sessions, and we can do it like we did last time and get chapter 3 in one time and chapter 4 another. That seems to work pretty good. Oh, Justice, you made it. Okay. I got the date right this time. All right, so any specifics, any problems, questions before we get started in chapter 3? All right. So let me share. I'm going to share the PowerPoint for chapter 3. There we go. And let's see. Get this out of the way. I got stuff in the way that you guys can't see. Here we go. Start the slideshow. Start the slideshow. There we go. Okay. Chapter 3 is on stoichiometry. So now we've come through learning the symbols, learning how to put compounds together and name them. And now we're going to start digging into what we can do with that information. And that brings us to stoichiometry. Stoichiometry is a way of accounting for all the materials that are consumed in a reaction and then produced in the reaction. And this accounting can be by numbers of molecules, numbers of atoms. It's more useful, though, usually to measure masses of reactants and producing masses of product, or volumes, particularly if it's a gas, volumes of reactants, volume, or it could be a mixture of the two. And then other types of reactions, and many types actually, occur in solution. So we need a way to account for whether it's mass or concentrations or volumes, the reactants going into a reaction and what comes out. And that's called stoichiometry. Just as a point of interest, I was interested in where the word came from. Turns out that there was a German at the end of the 18th century that actually coined the phrase and was the first one to use it. Name was Richter. And he based the term on a Greek word, stoichion, which related to a shadow line of a sundial. Now we call it sundials because in modern times the sundial is in a kind of a sweeping motion. But the earlier sundials were linear, and they had to be arranged in such a way, built in such a way that that linear threw a shadow across certain lines, and that's how they told time. And then of course the metric part means measure. So not that that helps any, but I'm always interested in history. Okay, the first problem we have to overcome is that in a reaction, we actually have atoms combined in molecules many times, reacting with other atoms or molecules, produce products. And these things are occurring at the submicroscopic level. Right, so we need a way to measure and account for what's happening in a reaction. And we do that by a process called counting by weighing. In other words, we find the masses of things and we can interpret the mass in terms of numbers of things, whether it's atoms, molecules, or ions. And that's called counting by weighing. And the way we do that is to use dimensional analysis. And you'll see pretty quickly what that means. So atoms are too small to count. I covered that already. And we, the objects that we're interested in, the atoms and the molecules, we have to assume that they behave as if each one were identical to the other. And what I mean by identical is that the masses are averaged. That'll become obvious in a couple of minutes. So, example. Here's something that we can actually see and get the concept. So let's say you have a pile of marbles, and the marbles weigh 394.8 grams. Zero grams. And how many marbles are in that pile? Well, in this case, we can count the marbles. So we assume that the marbles, let's just say the marbles represent atoms. So if these marbles, if 10 of them weigh that much, then we can get an average mass for each of the marbles. Now, each of the marbles does not have to weigh this value that we get. Right? It's an averaged value. So that gives us grams per marble. Right? Now that we know how much the average mass, you know, that's a typo, isn't it? That should be, wait a minute, the pile marbles, 10 marbles. Oh, no. Okay, I'm sorry. I got to read my own slide. First, we weigh a pile of marbles, and the pile weighs this much. But we don't want to count all the marbles in that pile. We want to find out how many marbles are in the pile. Or it's like the raffle where you have a jar full of jelly beans, and you're supposed to guess how many are in there. Well, if I had access to just a few of them, I could give you a pretty good idea of how many were in there. So this is how much the pile weighs. So we take out 10 marbles, and they weigh that many grams. Okay, now we can say that each marble in the pile has an average mass of 3.760 grams per marble. Okay, now that we know the average mass of the marbles, we can use that value to determine how many marbles are in the pile. Okay? So with this value, we can, this is our conversion factor for our dimensional analysis. So if we want to go from from here to total marbles in the pile. We want to convert grams to marbles. And we determined that each marble weighs 3.760 grams. Okay? So notice that if we pay attention to the units of measure, then we know that this mass has to be on the bottom to cancel that mass. And that leaves us with marbles per pile. So now all we have to do is divide this into that. And that should come out to 105 marbles on average. It may not be an exact value, but since you can't have a fraction of a marble, we're estimating the number of marbles in that pile. All right. So now when we're talking about atoms, how do we count the number of atoms in a pile? Or how do we count just a few atoms to get their average mass so we can find out how many atoms are in a larger mass of atoms? Because we can't actually pull them out like 10 atoms and weigh them. So that's the question. And that was the puzzle for the longest time. The answer is we use relative terms. We pick a standard mass for one isotope of one element and use that as our anchor point. And we're going to say that this standard isotope actually weighs 12 atomic mass units. And that isotope is equal to carbon. The isotope of carbon that has 6 protons and 6 neutrons is given exactly 12 atomic mass units to however many zeros you want, 12.0 infinity. That's our standard. And in addition to that, we use, in order to compare this one with others, we use Avogadro's law. Remember that? I told you that one, I think it was last review session, that as long as we know that we have the same number of atoms in this mass as we do in this mass, same volume, same temperature, same pressure, and then we expand upon that over time to include liquids and solids. So it's not an instant process, but over time we build up a body of knowledge that allows us to compare what we know to be exact numbers, same numbers of some element relative to carbon. Then we know that regardless of how many atoms are in each pile, we know the relative amounts of each one. So with that equality, and we know that this one is 12, then we can say with the equal number of atoms in this one, we can say that it is 14 or 16 or whatever it happens to be. Right? So we've got people that spend their entire lives determining Avogadro's number. And I'll give you some more information about the number in a minute. All right. So we're given the standard mass of the carbon-12 isotope is 12 atomic mass units. And everything else is based on that standard. There's another fly in the ointment, and that is, you may have guessed, that in nature, elements occur as a mixture of isotopes, and they don't all have the same mixture. Some of them, like, let's see, chlorine, are about 50-50, two different isotopes. But most of them have a majority of one isotope and then minor other isotopes. Like carbon-12 is the most common isotope of carbon, and you have a carbon-13 and you have a carbon-14. And those three make up 99.999% of all the carbon isotopes in nature. There are others, of course, but they're insignificant. So when we go to determine the average mass of an atom, we have to take into account a weighted average of isotopes. We can't just compare them to carbon-12 and expect that that mass comparison is going to be of a single isotope. So I'm going to show you how we deal with it. In this case, carbon-12 is this much. So really, for comparison purposes, we have to isolate. First step is to isolate these isotopes of carbon so that we can use them to compare. So as you may guess, there are certain people that spend their entire lives doing nothing but that. And then carbon-13 is a lesser amount, and carbon-14 is even less than that. So for all intents and purposes, in nature, carbon-12 and carbon-13 make up the lion's share of carbon isotopes. And we even compare this isotope to that isotope because this is the standard. Okay, so in nature, what we actually get is an average atomic mass. So many atomic mass units are assigned to the average mass of a carbon atom in nature. And the way you do that is similar to the way you determine your grade point average. So the lecture part of this course is worth 3 credits, and the lab part is worth 1 credit. So if you want to just get an average for Chem 101, 103 together, you would take 3/4 of the grade you get for the lecture and 1/4 of the grade for lab, add them together, and that would be an average value for Chem 101, 103. Or for your grade point average, you would take your courses and the grades that you get for them, and they're assigned numbers, like A is 4 credit units, B is 3, C is 2, and on down. And then you multiply those times the credit hours, and you add them together, and then you divide by the total number of credit hours, and you get a weighted average, which is your GPA. So it's a similar concept. The way we do it with elements in nature is we find out what the abundance is. And I'll show you how we do that in a minute. So 98% of the isotopes of carbon have 12 units, and 1.11% have 13.0034 units, right? This is a fractional value because it's based upon this anchor point. 12 is infinite zeros. So everything else is going to have fractional values. So we take the fractional equivalent of the percentages and multiply them by the atomic mass units. Sometimes you'll see that instead of the U, it'll be AMU. Okay, you can see it either way. And we take the fractional units, and this 12, isotope 12, contributes a large part of the total, and this is a minor part. That's what represented is 1.11% is 0.0111, and we do the calculation, and the average then is 12.01 to 2 decimal places. So if you look at your periodic table, then in the upper left-hand corner on this version, you'll see a value that's a fraction. This is 12.01, actually 0111. I always round it off to 2 places, 2 decimal places, because that's sufficient for our work. But those fractional values represent a weighted average for the isotopes of each element in nature. Now, over time, they'll change a little bit based on our precision of our instruments. The accuracy of and precision of our instruments will modify those values over time, and every 10 years or so, they republish them. But that's why I use 2 decimal places, because they never change at the 2nd decimal place. They always change at the 4th, 5th, 6th, 7th, 8th decimal place. So for our work, this is pretty much chiseled in stone. Okay. So just to drive the point home, naturally occurring carbon does not have a single atom that weighs 12.01 atomic mass units. There's no such thing. This is a weighted average of all. It's like counting by weighing. We found out how much one atom on average weighs. And we can use that to determine the mass of a whole bunch of atoms. And conversely, we can say if we weigh a certain amount and we get a weight, then we can find out how many of those that we have. And it's all dimensional analysis. Okay, so that was for carbon. Now, how do we tell how many of each isotope we have? Well, it takes some pretty sophisticated instrumentation to do that. And one piece of equipment that's very useful is the mass spectrometer. So when we say spectro in any instrument, we mean we're splitting it apart into pieces that are different based on some common factor. A light spectrometer will take white light, say, from the sun, and you can split it apart in the different colors. Well, actually, for the sun, you have lines, but that's another story. But for a mass spectrometer, we use mass as the determining factor for splitting our groups apart. So what we do is we vaporize the sample, then we ionize it, because ions can be controlled. Neutral atoms are more difficult to control. And then we accelerate it through an electric field. And at the same time, we run it through actually these holes are a lot bigger than they should be. Run it through 2 slits. And what that does is if you have a source over here and it's sending out ions, right? Some of them are going to come through the hole, but they're going to come through at angles. So they won't be quite as divided, as the original. But if we put a second slit out there, then only the ones that have a proper trajectory through this hole and that hole will come out straight. And we want that straight beam because we're going to take that beam and manipulate it. And in this particular type of mass spectrometer, we manipulate it in a magnetic field. So we have a magnetic field, and it will cause the ions to change direction. And since the magnetic field is constant, then the force that's applied to a singly charged ion is the same for every ion. But since every ion doesn't weigh the same, right? They're different isotopes, so they have different masses. The heavier ones are going to be bent less because they have more momentum, right? They can resist the force that's trying to make them change directions. So the heavy ones are going to end out here with the least bend, and the lighter ones are going to end up here with the most bend. And if you calibrate your instrument correctly, you can say, well, this one is carbon 12, this one's carbon 13, this one's carbon 14. No, other way around, excuse me. I'm contradicting myself. The heaviest one is out here. Carbon 14 would be here, 13 and 12, and the lighter ones would be down here. And with the advent of modern electronics, we can count individual strikes on the detector. And each strike represents an ion. And the electronics can count how many strikes occur per second, and you can ratio. So the more strikes, the more atoms, or the more ions. Okay, so that's how we determine isotopes of naturally occurring elements. First, you have to have a pure sample, right? That's essential. Then you can tell the difference between the isotopes. Okay, so let's take this example. You're given an element, and you're said, and you're told that it has 62.6% of an isotope that has a mass of 186.956 atomic mass units. And it's a mixture with two isotopes, and the other isotope is 37.4% with a mass of 184.953. All right, so let's just assume that that was determined using that mass spectrometer. Now, what's the average atomic mass? Right, so we would take 186.956 atomic mass units and multiply it by its abundance. So the decimal equivalent of 62.6 is 0.626. And then the other isotope is 184.953. Uh, 374. Actually, I got another right there. There we go. So you're going to get a value here and a value here, which will be less than these by that factor. And then you add them together. And that's your average atomic mass units for this element. Right? So we should get 186.2 rounded off. Okay. Now, how can we use that to determine what the element is? Well, we've already, let's see, we've already shown that if you know the Z value or the atomic number, you know how many protons there are, that nails the element down without any ambiguity. So you can just look along here if we knew the number of protons, but we don't. what we know is the average atomic mass for this element. And you'll notice also that in this at the upper left-hand corner, the mass of the average atomic mass of each element goes up as you go from left to right and top to bottom. So you can get pretty close just using this value, 186.2. So we look along here, see if I'm still in the frame, and we see it's getting bigger and bigger and bigger, and just keep going until you find close to what you want. There's W. What's W? Tungsten is 183.85, so it's not quite heavy enough. The next one, 186.207, is probably a good candidate. So let's go beyond it and say osmium, is 190. So we bracket it in. It's probably rhenium. Right? So it's kind of like a detective story. Put all the evidence together, and you do like Sherlock Holmes said. You get all your facts together, and you eliminate the ones that are impossible. Then whatever's left, no matter how improbable, is the correct one. So that would be rhenium. Now, you didn't have to memorize that one. I'm pretty sure I didn't make you memorize that one. But that's the one. And you can use atomic mass, average atomic mass, to determine the element. There are a couple of places in the periodic table where the average atomic masses are very close together. So in those cases, it might be difficult to determine the element based on just the atomic mass average value. For instance, argon is 39.948, and calcium is 40.08. That's very close. But what do we know about argon and calcium? Well, you may know the average atomic mass. What do you know about its state? Argon is going to be a gas. Calcium is going to be a metal, right? Solid. So you can use that information to break the tie. Okay, so we need a value to count the number of atoms or the number of things in a collection or a mass that we've determined. Because we know that atoms are very, very, very small, don't weigh much individually, which means in order to get a large enough number of them to register on our balances, we need lots of them, like billions and billions of them, in order to have enough to weigh on our balance. So counting individuals, like saying billions of so many, is a little tedious, and easy to make mistakes with that large a number. So we've got a new unit of measure we call the mole. And the mole is just a number of things, but it has an exact value. Right? And we base it upon the number of carbon-12 isotope atoms that is equivalent to exactly 12 grams. So if we have 12 grams of carbon-12, we have exactly 1 mole of carbon atoms. So we're not only using the carbon-12 isotope as our single atom standard, we're using a certain number of carbon atoms, isotope 12, to determine another unit of measure, which is the mole. Now, that unit has a value, and it's equal to 3 decimal points, 6.022 times 10 to the 23rd. Right? So that's a huge number. And we give it this name, Avogadro's number, in honor. Now, Avogadro didn't come up with a number. We're just honoring him because it's based upon his earlier work that we are able to make this determination. So Avogadro's number is 6.022 times 10 to the 23rd atoms, ions, molecules equal to 1 mole. In fact, it's just a number, right? So we could just as easily say it's a mole of chickens. And it would be 6.022 times 10 to the 23rd chickens is a mole of chickens. Okay. So the carbon-12 isotope, if we have exactly 12 grams, gives us a mole of carbon-12 isotopes. But in nature, we know we have a mixture of isotopes. So how much does a naturally occurring mixture of carbon isotopes weigh if we have a mole of them? Well, as it turns out, a mole of naturally occurring carbon atoms weighs 12.01 grams. All right. So that means that the value that you see in your chart here, the average atomic mass, could represent the average atomic mass units for one atom, but it also equals the mass in grams of a mole of those mixture of isotopes. Right? So that value we can use as a conversion factor. 1 mole, and we abbreviate mole by just dropping the E. Don't ask me to make sense of that. That's just the abbreviation. MOL without the E is the abbreviation for mole with the E. So 1 mole of carbon naturally occurring is 12.01 grams. And remember, conversion factors are equal to 1, which means the numerator is equivalent to the denominator. So if we needed grams on top and moles on the bottom, you can flip it. No problem. You're still ending up with 1 divided by the other is equal to 1. And in fact, when another name for that number in your periodic table is molar mass. So 12.01 grams per mole is the molar mass of naturally occurring carbon. Chlorine. Chlorine will be 35.45 grams per mole. Okay? You can do that for any element in the periodic table. That number will have grams per mole affixed to it. All right. Any questions so far? All right. And I've answered this question. Why 12.01 and not exactly 12? That's because 12.01 represents a weighted average of naturally occurring carbon. Okay, so now let's use it. Let's use this new information to answer a question. How many iron atoms are contained in 4.48 moles of iron? All right, this is dimensional analysis. This is our starting point. Where do we want to end up with? We want to end up with numbers of atoms. So we want a conversion factor that will give us atoms. Okay? So if this is going to be in the numerator, it has to be in the numerator here. And this is moles to cancel. So all we need is what's the relationship between atoms and moles? It's Avogadro's number. 6.022 times 10 to the 23rd. So all you have to do is, after you cancel the units and know that you're ending up with the right unit of measure, now it's just crunching numbers. 4.48 times 6.02 times 10 to the 23rd. All right. And that's 2.7 times 10 to the 24th iron atoms. Okay? Dimensional analysis. Keep track of your units. A large part of chemistry is nothing more than unit conversions. Now, of course, there's more to it than that, but you can solve a whole host of problems in chemistry if you pay attention to the units. You know where you're starting from, you know where you want to go. In between is conversion factors. And they're going to come back time and time and time again. Okay, so this is the molar mass of naturally occurring nitrogen. You can look it up on your periodic table, right? You just look over here to find nitrogen, and then you find wherever it happens to be. It depends on the periodic chart of the table. This one is in the upper right-hand corner, and I rounded off to 2 decimal places at 14.01 grams per mole of naturally occurring nitrogen isotopes. And you can do that for any element. The question is, what if you don't have an element? What if you have a compound? Is it possible to determine the molar mass of a compound? And that's a rhetorical question, because the answer is yes. All you have to do is add the molar masses of each of the atoms in the formula of the compound, right? So in this case, for water, for every 1 mole, and I forgot to subscript that one, for every 1 mole of water, you have 1 mole of oxygen and 2 moles of hydrogen. So 2 moles of hydrogen is 1.008. I should have rounded that to 101. And then 1 mole of 1 mole of oxygen, which is 16, rounded off to 2 decimal places. So we got 1 of these for oxygen and 2 for the hydrogens. So the molar mass of water is 18.02 grams per mole of water. And you can do that with any compound. You just have to be sure that you know how many of each element is in the formula before you do your calculation. So if we have something complex like this one, how many bariums do you have? Well, there's just 1. So there's the barium molar mass. How many nitrogens do you have? Well, nitrate is inside the parentheses with a subscript of 2. So you have 2 nitrogens. And you have 6 oxygens. 2 times 3 is 6. Then you can add that up, and this is the molar mass of barium nitrate. All right? So what does that mean? That means if you have 261.35 grams of naturally occurring barium nitrate, you know that you have 1 mole of molecules. If you have 1 mole of molecules, how many moles of nitrogen do you have? 2 moles. If you have 1 mole of barium nitrate, how many moles of oxygen do you have? You have 6 moles. Okay. All right. So here's an easy question, and test taking technique will answer this question for you. and you don't even need to do the calculation. Which of the following is closest to the average mass of one atom of copper? We know copper atoms are very small. None of them are going to weigh a gram each or a multiple of a gram each. So, you know, test-taking technique tells you that the answer is E. It's the smallest one, the very smallest number. But you can do the calculation. You've got one copper atom, and how many moles of copper atoms do you have? Well, this is so many copper atoms per mole. So the atoms cancel and leave you with moles. Then you can convert moles to grams using the molar mass of copper. Right? Units cancel, and you're left with that value for your grams. All right. So how many copper atoms are there in 63.55 gram sample of copper? You don't even have to do a calculation. You're going to need the molar mass to be sure, but if you look it up, if you look up the molar mass of copper here, which is, let's see, right there, how much does a mole of copper weigh? 63.55 grams, which means if you have that much, you have exactly 1 mole, or 6.022 times 10 to the 23rd copper atoms. And just to drive this point home, if you actually made that measurement in the lab, 63.55 grams, and you knew that you had that much copper, are you sure to have exactly 6.022 times 10 to the 23rd copper atoms? The answer is no, because every measurement has uncertainty. You're pretty close, right? And for calculation purposes, you may just have to use it and assume that it's true. But always in the back of your mind, recognize that whenever you make a measurement of this value or any other value, there is uncertainty. And that's why this value keeps changing every 10 years or so, just like molar masses. The value of Avogadro's number slightly changes because our instrumentation and accuracy, precision of measurements is improved. So they make another measurement and determine that it's different to about the 10th decimal place. Okay. So here's a concept question. Let's say you have 100 grams of each magnesium, zinc, and silver. 100 grams of magnesium, 100 grams of zinc, 100 grams of silver. Which contains the greatest number of atoms? All right, if you got the same mass, then ask yourself, which one has the heaviest atom? The one with the heaviest atom will be able to accumulate 100 grams of sample with fewer atoms, right? So conversely, in order to get a 100-gram sample for the lightest element, you need a lot more atoms because each atom weighs less. So to answer the question, which one contains the greatest number of atoms? The one that has the lightest atom. So you look at the periodic table and you find the molar mass for the lightest one. And if you look it up, the lightest one is going to be magnesium. Okay? That's why magnesium is incorporated into a number of different alloys, because it is extremely light. But still, It's a metal, and it can be used in an alloy to maintain the strength of the metal, but make it lighter. In fact, some parts in specialty cars, so racing vehicles, are forged, or they could be cast from pure magnesium, and they're very light. I would imagine that magnesium is used extensively in aluminum alloys for aircraft because it is so light. It's even lighter than aluminum. Okay. Now, for this question, we want to rank the following according to the number of atoms, greatest to least. So the solution to this problem is actually, you don't have to do the calculation. You can if you want, but we can save ourselves time and effort if we know we have 107.9 grams of silver, 70 grams of zinc, 21 grams of magnesium. Let's convert those to moles. So 107.9 grams of silver. Okay, here's silver, right here. And its molar mass is 107.87. So rounded off, 107.9. That means we've got exactly 1 mole of silver. Okay? How about 70 grams of zinc? Well, let's see. Zinc is right here, and its molar mass is 65.39, which means 70 grams is more than 1 mole. Okay? Magnesium, we just determined that one as 24.3, so we have less than a mole of magnesium. So now it should be obvious that we can arrange these from greatest to least. Zinc will be first, then silver, and then the least, magnesium. Now, if we were given 5 or 6 different elements with these numbers, it may be necessary after doing this determination to break the tie between some. 2 of them might be less than 1 mole, and the other 2 might be greater than a mole, and then you have to break the tie. Okay, now we're getting more complex with our problem solving. If we have 100-gram sample of each of these compounds, rank them from greatest to least number of oxygen atoms. All right, for this solution, I go back to Henry Ford, the assembly line. What you want to do is the same calculation for each one of these. So once you get it set up and you got the right terms plugged in, the calculation is the same, just with different numbers. So that shortens the workload and helps avoid errors. So let's see. I'm going to make some more room here. Well, maybe, maybe not. All right. Set that aside to dry. Now, I need, let's see, I want to keep. I'm going to have to move this over some, because I'm going to expand my board, because I need more room. Expanded a lot. There we go. Okay, everything's in frame. So what do we have? 100-gram sample of each one. water, we have water, and we have dinitrogen monoxide, otherwise known as nitrous oxide, laughing gas. Then we have C3H6O2, which I think is propionic acid. Okay, and then we have carbon dioxide. All right, we're starting out with 100 grams each. Right? So that's the same for each one. Okay, building our assembly line. What do we need to know? Well, we need to know the number of moles of each compound first, and then the ratio of atoms of oxygen per molecules. So how do we find the numbers of each? We use the molar mass of each one. Right? We got to cancel the grams, okay, and leave us with moles. So are the grams going to be the same for each one? The answer is no. We're going to have different number of grams for each one because they're different compounds. So how about water? We did that one a couple of slides ago. Water is 18.02 grams per mole. That'll give us moles of water. So let's say we've determined that one. That's moles of the compound. So how many for every mole of compound, how many moles of oxygen do you have? In water, it's 1 to 1. For every mole of water, you have 1 mole of oxygen. All right, so that cancels, that cancels. And now all we have to do is crunch the numbers and we find out how many moles of oxygen there are. So we do the same thing for each one. Nitrogen, dinitrogen monoxide. All right, so I'm gonna get my calculator. How many oxygens do we have? 1. And you look up on your periodic table, 1 oxygen is 16. And we have 2 nitrogens. Each nitrogen is 14.01. So 14.01 times 2 is 2802, and then plus what we had before is 4402. Okay? Now, how about this one? What's the ratio? It's still 1 to 1, right? 1 oxygen for every mole. 1 mole of oxygen for every mole of nitrogen, dinitrogen monoxide. Okay? How about this one? C3H6O2. All right. We just did carbon. 12.01. 3 times that. Hydrogen. Look up hydrogen is 1.01. So 6 times that is 6.06. And then 2 oxygens, 16 each, is 32. So that one's 74.09. So you can see why I want to do it assembly line. Because once I know the order of actions, then I just have to fill in the exact numbers and do everyone the same way. Just like we were building a Model T. Carbon dioxide. Oh, wait a minute. Oxygens. Oxygens per compound. In this one, we have 2 oxygens for every molecule So for every one compound, we have 2 oxygens. Carbon dioxide, what's its molar mass? Well, carbon is 12.01. And we have 2 oxygens, which is 32. 16 plus 16. So that's 4401. Okay. Now we do the oxygen. So we have 2 oxygens for every mole of carbon dioxide. There we go. Now we've calculated how many moles of oxygen atoms. And notice that we're going to rank these in order of greatest to least number of oxygen atoms. Do we need to determine the actual number of oxygen atoms? Like use Avogadro's number? No, not if you're going to put them in order. If you're going to put them in order, all you need is the number of moles, because moles is a measure of numbers, right? So you save yourself the extra step of determining actual numbers of atoms and just stop at moles. So now our calculations would be 100 divided by 1802 times 1. Which is 5.55 moles of oxygen. Nitrous oxide, 4402. Oops. 100. That's 2.27 because it's 1 to 1. Okay. Propionic acid, 100 grams, 74.09. Divide. Now we have to multiply by 2 because of this ratio. That's 2.70. And carbon dioxide, 44.01 times 2, 4.54. Okay, order of greatest to least. Greatest, this one, next one, next one, last. Okay, so we should have water, carbon dioxide, propionic acid, and nitrous oxide. That's how we solve that problem. According to Henry Ford. Okay, any questions? We're going to use Henry Ford again for a different type of problem. But the format is the same. If you've got to make a comparison, or you're going to have to do several calculations that are all the same way, then just set them up like that, so that you know that each one is calculated the same way. You just have to fill in the right numbers in each of the conversion factors. This is the author's idea of problem solving. Where are you going? Another way of saying that is, what's the question? When you read a word problem in a test or in a homework problem, there's a lot of blue smoke in there, a lot of information that you may not need. What you've got to do is pick out the question. What is it asking? Then you look at the information that you're given, and do you have all the information you need? You may have to go look for some information, like you may need a periodic table, or you may need the useful information table that I give you at the end of every exam. And then you follow that procedure with the information that you're given to solve the problem. And then you do a reality check. You look at the answer and say, is that answer reasonable? That's why I use estimation a lot. You know, just run it through your head and just round things off and do a quick estimation and say, is your answer in the same order of magnitude, say, as the estimate? Reality check. When I was in graduate school at Louisiana State University, my next door neighbor was a student in mechanical engineering. And he used to tell me stories about students who had studied the chapter and knew the chapter material backwards and forwards. And they would go into an exam, be given a problem, and they would try to solve the problem with what they had learned only from that chapter. In other words, it's like everything before had been forgotten. And they would shoehorn the values into what they knew, and of course get the wrong answer. And the wrong answer would be something like 10 orders of magnitude too big for the problem if you looked at it reality. You know, the force applied in this particular case should be maybe 100 pounds or 100 newtons or whatever the units of measure. But they come up with like 10 to the 6th or 1,000,000 pounds or 1,000,000 newtons. And they just put the answer down because they didn't know any different. If you do a reality check and say, what is a reasonable answer? Then you would know right off that you got the wrong answer and you ought to go back and recalculate. So that's why the reality check is so important. It can save your butt in a number of situations. Okay. So let's see. I'm running down the wire. We're probably not going to finish this chapter today. So let me see. Percent. All right. I'm going to keep moving until I'm out of time. Mass percent of an element. Why do we need to know this? Because when a bench chemist analyzes a new compound for its composition, they always produce as the first result a mass percentage of the element in the compound. So what it means is it's simply the mass of the element in the compound divided by the total mass of the compound that was analyzed times 100. It's very simple. That's the mass percent of the element. Now it's what you do with that information that's important, because you can't stop there. Unless if you already know the formula of the compound, yeah, you can stop there, and it's just a check on percentage by mass. But if it's a new compound and you don't know the molecular formula, then this is the first step on the way to determining the formula. And I'm going to show you how to do that maybe next time. It probably won't have time now. But you can go both ways. You can go into the lab, determine the mass percent, and work your way to the formula. But you can also take the formula, if you know it, in this case iron 3 oxide, Fe2O3, and you can determine what's the expected mass percent of that compound. All right. Well, first of all, is it written correctly? Iron 3 oxide. Well, let's see. Iron 3 oxide. So we know that the iron is going to have a 3+ charge, right? How about the oxygen? It's always 2-, right? It's a chalcogen. They're always 2-. So the ratio should be 2 here and 3 here, right? Cross multiply. 6 minuses, 6 pluses, balanced. So yeah, it's written correctly, Fe2O3. Why do we need to know that? Because we're going to use the formula to determine the mass percent of each element. So here's how you do it. You just assume that you have a mole of the compound. So how many moles of iron are in that compound? Well, there are 2. So how much does 2 moles of iron weigh? 55.85 times 2. Now, how much does the entire compound weigh? We did that one before. Well, we didn't do this one, but we did compounds. 2 irons plus 3 oxygens is the total for 1 mole. So now you have how much does the iron weigh, how much does the compound weigh, divide by 100, 69.94% is iron. Now, if you need to know oxygen, you can do the same thing. Or since iron and oxygen are the only 2 elements, then it should be 100 minus 69.94 would be how much oxygen by percentage. Okay, well, let's see. I guess it's 1:45, and we're about halfway through. But the topics in this chapter are so important, I wanted to be sure that we got through them thoroughly. So let's say we'll pick it up here on Tuesday, I guess. This is Thursday. So we'll pick it up here on Tuesday and finish this chapter out. And if there's time, we'll start on chapter 4. If not, we'll pick up chapter 4 on the following Thursday.